In the last video, we derived a very important constant acceleration equation. So just to remind you, that was vf squared equals v initial squared plus 2ad. And we used it to find the v final when the ball was thrown up and off the cliff. Okay. Now, the last question that we looked at, just to remind you, was which one of the balls is taking longer to hit the ground or is in the air for a longer time. So we're going to use another equation in order to solve those. So if you recall, originally when I gave you the dropping problem, I told you how fast the ball was going when it hit the ground, and we used that to figure out that the time it took to hit the ground was 10 seconds. Well, I'm going to do that again, but we're just going to assume that we don't know the time. Let's just say we know the height of the cliff only, okay? So we're asked, in this case, to find t, and the information that we're given is we know we're on a 500-meter cliff. So remember, our displacement is 500 meters down, and our acceleration is negative 10 meters per second squared because it's gravity. And the other thing that we know, even without being told, if it's a dropping problem, is that my initial velocity is 0 meters per second. So we're going to try and derive an equation where we don't know how fast the ball is going when it hits the ground. So equations that we have are d equals v average times time, okay? And we know that v average is v final plus v initial all over 2. And remember, that is only for constant acceleration, which we're dealing with here because it's gravity. So if I sub that in just like I did before, I get that d equals v initial plus v final all over 2 times t. Okay? And we want to eliminate v final, right? Because we don't know what v final is in this case. We want to solve for t. We have d in there. We have a, which isn't in the equation yet, and we have v initial, but we don't have v final. So we have to find some way that we can sub out v final. Okay? So remember that acceleration is v final minus v initial over t. So if we solve this for v final, I'm going to multiply by t on both sides, and so I get at equals vf minus v initial. And then if I just add that to both sides, I get at plus v initial equals vf. So by rearranging this equation, I can now sub in this for v final. All right, so let's go ahead and do that, and it's going to be a big algebraic mess. Again, I'm deriving these for you so you don't have to do them on your own later, and we can just memorize them, but I'd like for you to see where they come from. So we have v initial plus at plus v initial all over 2 times t. Okay, so if I multiply the t through here, I get t in every term, and if I add those two, let's see, I'm just jumping some algebraic steps here, so we're going to have 2 VOs times t, okay, plus divided by 2, so it's 2 then divided by 2, so I actually get v initial times t plus at squared over 2, or 1/2 at squared. This is the second of our derived constant acceleration equations that we want to memorize. Okay, so we have this one here, and we have those, and that one there. Okay, on top of our other equations. Okay, so let's go ahead and use this to solve for the time, and we know it should be 10 seconds, right? Because we already figured it out before. But let's use this equation this time. And then we're going to use this same example, or the same equation, given the throwing the ball up in the air example. Okay? So we just need to plug and chug. What's important to note here is that when the v initial is 0, this term cancels out. So we actually get that d equals 1/2 at squared. And you'll use this equation a lot because any type of dropping problem where we have an initial velocity of 0, that term cancels out. So we have negative 500 is equal to 1/2 of a, so a half of a negative 10 is negative 5t squared. Divide by negative 5 on both sides, and you get 100 equals t squared, or t equals 10 seconds. Right? Alright, so we predicted that if we throw the ball up and off the cliff, that it's going to take more time for it to hit the ground. So we predict that throwing the ball up in the air will be more than 10 seconds to hit the ground. So let's go ahead and use this equation in order to solve the problem where we're throwing the ball up and off the cliff. Okay, so recall again, we're going to be solving for time, and we're given acceleration, which is negative 10 meters per second squared. We're given our d. Remember that displacement is the same whether you throw the ball up and off the cliff or down off the cliff, because the change in position is the same. So we're still going to have a displacement of negative 500 meters. Okay, and then what else do we know? Oh, we remember that the initial, I'll use the same velocity as we had from the last example, was 30 meters per second. Remember when we were throwing it up off the cliff at 30 meters per second. Okay, so our equation that applies here is that d equals v initial t plus 1/2 a t squared. Okay, and let's go ahead and plug in our numbers. Okay, so we have negative 500 is equal, and I'm just going to ignore units right now so you can see what happens here. Times 30t plus 1/2 of a, that's going to be a negative 5t squared. Okay, now if you look at this, you might recognize that this is a quadratic. So if I just solve for 0, so add 500 to both sides, and I'm going to flip this because to me seeing a quadratic makes more sense when it's the squared term is first. So it's going to be negative 5t squared plus 30t, and then adding this to the other side, plus 500. Okay, so if we remember that our quadratic equation, we have to remember our quadratic equation is that the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Okay, and my a term is negative 5, not to be confused with acceleration. My b term is 30, and my c term is 500. And again, we could reduce these. Okay, and then if we just plug them into the Pythagorean theorem, or the quadratic equation, I'm not going to go through all that. You actually get 2 answers for t when you do this. Okay, so if I plug all that in, I get some negative number, but time doesn't go back. Like we never have a negative time, and the reason is because time is a scalar, and it doesn't have a direction. Okay, it's always positive. So we actually get that t equals 13.45 seconds. Okay, which is more than my original. Where does that negative number come from? Well, essentially what it means, if we look at the path of a ball that's thrown up and off a cliff, it accelerates. First, you throw it up, and it's being slowed down, decelerating by gravity, until right at the top, the velocity is 0. Okay, for a moment it stops and then changes directions, and then it accelerates back down towards the ground. Okay, now if you look at this, you might notice that this path is a parabola, which is what, if we were to graph a quadratic equation, we get a parabola. So where does that negative number come from? Remember that this number here that we solve for is actually the x-intercept. So if we go back over here, we're going to have some negative time, okay, as if we had thrown the ball some point in the past from the ground. Okay, so I hope this makes clear, and I know I kind of went through those derivations sort of fast, but what's most important to remember is that we have these specific equations. Vf squared equals V initial squared plus 2AD, and that D equals V initial T plus 1/2 AT squared.